Think about it for a second. From the apps on your phone to the systems that run, well, pretty much everything, software is the invisible architecture of our world. But how do we get from a simple idea to a complex, reliable system that millions of people depend on every single day? That journey, that's the heart of a discipline that goes way beyond just writing code. It's called software engineering.
So here's a great way to think about it. Writing a quick script for yourself? That's kind of like building a garden shed. It gets the job done, it's just for you, and hey, if it's a little wobbly, who cares, right? But building an application for thousands, maybe millions of users, that's like building a skyscraper. You need a plan, a team, and a disciplined, professional approach to make sure it's safe, reliable, and definitely won't fall over. That's the core difference we're talking about.
All right, so if we're going to build that skyscraper the right way, we need to understand the blueprints. And that means we've got to get on the same page about two core concepts: what we actually mean by software and what really makes this an engineering discipline.
See, in the professional world, software is so much more than just lines of code. It's the whole package, the whole shebang. It's the user manuals, the design documents, all the little configuration files, everything that's required to make that program work correctly for the people who are actually going to use it. The code is just one piece of a much, much bigger puzzle.
And that brings us to the big one: software engineering itself. The most important phrase here is engineering discipline. This is not about being a lone genius coder in a dark room. It's about systematically applying proven theories, methods, and tools to build useful products that work within real-world limits, like budgets and deadlines. It covers everything from that first spark of an idea all the way to keeping that system running years down the line.
So if we're going through all this trouble, what's the end goal? What really separates a professional, engineered product from just a quick personal project? Well, it all comes down to a few key qualities or attributes that all good software should have.
Let's break these down real quick. First up, maintainability. Can you actually change the software later to meet new needs? Or is it a fragile house of cards that'll collapse if you so much as look at it funny? Then, dependability and security. Is it reliable? I mean, you absolutely demand that your banking app is dependable, right? Next is efficiency. Does it respect your computer's resources, or does it drain your phone's battery in 10 minutes? And finally, acceptability. Is the software actually usable for the people it was built for? A brilliant piece of code is totally useless if nobody can figure out how to use it.
But why did we even need this formal discipline in the first place? For a long time, there was no such thing as software engineering. There was just programming. Let's take a look at the moment in history when that absolutely had to change.
This right here is the turning point. In the late 1960s, the industry was facing what they called a software crisis. These huge, ambitious projects were consistently failing. They were late, they were way over budget, and honestly, they were dangerously unreliable. The old, informal, garden shed approach just couldn't handle skyscraper-sized problems. This crisis is what forced the entire industry to get serious and grow up.
And this chart gives you a real sense of that modern engineering mindset. Get this. For many big projects, a huge chunk of the budget, sometimes 40% or even more, isn't for writing new code. Nope, it's for testing and validating what's already been built. Imagine if a car company spent nearly half its budget not on building cars but on crash testing them. That's the level of rigor we're talking about here.
Now, no matter what the project is, whether it's a simple website or the software that runs a spacecraft, the engineering process can almost always be broken down into 4 fundamental activities. These apply to pretty much everything.
It all starts with specification, which is just a fancy way of saying, let's agree on what the heck we're building. Then comes development. That's the actual design and coding part. After that, and this is crucial, comes validation, testing the thing to make sure it actually does what the customer wanted. But it doesn't stop there. The final and honestly often the longest phase is evolution, because successful software lives on for years and years, constantly being updated to meet new challenges.
Okay, so you have these 4 activities, but you can't just do them in any random order. They have to be organized into a coherent plan. And this brings us to what are called process models, which are basically the different blueprints or recipes engineers use to manage a project from start to finish.
And there are lots of different blueprints to choose from. You've got the classic waterfall model, which is super linear. It's like building a house. You lay the foundation, then you put up the walls. You do each step once in order. Then there's incremental development, which is more like how mobile apps are made. You release a basic version first, and then you add new features with each update. And reuse-oriented engineering? That's kind of like building with Legos. You're snapping together a new system from existing, pre-built components.
But being a great engineer isn't just about the technical stuff. Not at all. Because software has such a massive impact on our daily lives, there's this incredibly important non-technical side to it: professional and ethical responsibility.
This quote really gets to the heart of it. The message is simple. The work of a software engineer has real-world consequences. The systems they build can do amazing good for people, but they can also cause serious, serious harm. That kind of power comes with a profound responsibility.
So, to help guide these tough decisions, professional organizations created a code of ethics. And this isn't just some vague advice. It gives clear principles. Always act in the public's best interest, be honest with your client, build the best quality products you can, and maintain your professional integrity, even when it's hard.
And that really brings us full circle to the core takeaway. There's no magic formula, no single best way to build every piece of software. What separates a real software engineer from just a coder is the ability to look at a problem and choose the right tools, the right process, and the right techniques for that specific job. So we've gone from a simple bit of code to this huge, complex engineering discipline that builds the very infrastructure of our modern lives. As this technology gets even more powerful and woven into every single thing we do, it leaves us with one final and really crucial question. It's not just about how we build this new world, but why we're building it, and what our ultimate responsibility is to the future we're all creating together.